Hi, welcome to Lecture 2 of Week 2 of GEOEL221 on Metamorphic Rocks, Part 2. Last lecture I introduced the pressure-temperature diagram, or the PT diagram, that illustrates temperature and pressure in the Earth's crust associated with metamorphism, and each zone illustrated on the diagram experience similar mineralogical effects or development of metamorphic minerals during metamorphism. Now the question is, how do the rocks actually get there? To answer this question, we can look at PT paths, and this is a very simplified graph, but it illustrates the life cycle of a metamorphic rock. And by plotting this life cycle on a PT graph, we can illustrate the rock's history. The life cycle of a metamorphic rock starts after diagenesis near 0, of pressure and temperature, follows the steep curve down during burial, which is called prograde metamorphism. With enough burial, we have an increase in temperature or heating. We'll reach a maximum pressure point and carry on with retrograde metamorphism, all the way back to 0 pressure and 0 temperature conditions. This process is, as we discussed last class, controlled by plate tectonics. Take the example of a subduction zone with regional metamorphism. The burial and heating is the collision and mountain building event at the convergent plate boundaries, and exhumation occurs after that through uplift and erosion of the mountain belt. If we look at the same PT path in a bit more detail, this is a slightly different version of that same pressure-temperature graph. In this case, note that pressure and depth are increasing on the y-axis. Looking at the example path shown in red, if we start at diagenesis of a sedimentary rock, the example shown on the bottom left photo is an outcrop of limestone. As this limestone gets buried, we have prograde metamorphism. Eventually, it'll reach a high pressure temperature conditions where the limestone will metamorphose into marble, like the image shown on the top right of the slide. And then through exhumation, going back down to 0 of pressure and temperature, we can visit this outcrop of marble at ground surface. So what else happens during exhumation? This is a very exciting time for brittle processes where joints, fractures, and faults form, and sometimes with hydrothermal activity and water enrichment, we can have minerals deposited on these brittle fractures. Now, I'll talk more about joints, fractures, and faults a bit later, but I wanted to introduce this concept within the metamorphism cycle to give you a broad picture of what's going on. Let's have a look at the metamorphism progression starting from shale as a sedimentary rock through to slate, schist, and gneiss. This metamorphic progression follows the red arrow on the PT diagram on the top right. That simply shows an increasing metamorphic grade. As the shale goes to slate, we have clay minerals developing and growing. Towards schist, we have the development of micas, plus or minus chlorite, and other minerals. And the addition of gneiss, we have mafic and other minerals that form. Here's a convenient diagram that lays out the mineral assemblages during shale metamorphism in a bit more detail. On the low-grade side on the left of shales and sandstones, through to the gneiss on the right, what minerals are present in each of these stages. For example, the clay minerals are present in shales and slates, but by the time the metamorphic grade gets high enough, going from slate to phyllites towards schists, the clays disappear because those elements are used to form micas. Chlorite has a short window in which it appears during slate and phyllites. Quartz exists throughout this entire metamorphic series. As we get into schists, we start to see the formation of biotite and garnet and starlite, and we get into the very high grade of gneiss, sillimanite, and metamorphic potassium feldspar. And it's important to note that all gneisses are considered high-grade metamorphic rocks. Speaking of gneisses, how exactly does gneissic banding or layering form? During shearing and compression, the minerals stretch through ductile deformation during the recrystallization of the protolith minerals and the growth of new metamorphic minerals during prograde metamorphism at high pressures and temperatures. There's two example sequences on the bottom. The example on the left shows a protolith that has large black inclusions. During shearing and compression, this rock would get flattened, followed by folding, and eventually the noses or hinges of the folds get sheared off and may no longer be visible in the present day outcrop. The example on the right shows an initial state of more of a bedding type of structure, and as you go through stages from stage 1 to stage 5, you can see initially the bedding gets folded. There's some thickening and thinning of the limbs and hinges until the initial bedding gets transposed and cut off from each other. And into stage 4, you start to see a very similar picture of the present day outcrop shown on the left example. We talked a bit about metamorphic recrystallization in the last lecture, but I'd like to revisit it here. Remember that metamorphism not only changes some of the mineralogy, but it can also rearrange grain boundaries even in the minerals that persist. The example shown here, remember, is a sandstone on the left showing rounded quartz grains with pore space, cement, and matrix in between, compared to the photo on the right, which illustrates the quartzite, or the metamorphosed quartz, crystals that are now interlocked, have angular grain boundaries, and the pore space and matrix and cement have disappeared. In addition to this recrystallization, when we have regional metamorphism, we have folding and faulting that occurs. Folding at all scales is common, and in fact you will see folds at mountain-sized scales repeated in minerals at a hand sample scale and even a thin section scale. The metamorphism and deformation occur all together in the rocks in the region. So if you deform a rock at high pressure temperature, you will have the grain boundaries realigning, and the grains may also elongate or get flattened depending on the in situ stresses, or in other words, depending on the ground pressures being applied to the rock during metamorphism. We may see this in the field as lengthened or flattened features. In the photo on the right, you can see a metaconglomerate, or a conglomerate that has been metamorphosed and squished horizontally to flatten what would have been originally more spherical clasts. In addition to the flattening and elongation of particles, you also have the development of platy minerals like micas that grow perpendicular to the applied stresses as they grow. And this process generates what's called schistosity. And schistosity is the primary metamorphic texture of its namesake, a schist. As you get squishing and squashing of rocks through metamorphism, you can sometimes develop a foliation. We talked a bit about foliation last class, and we'll get into it in more detail this week. One example of a foliation that is the result of metamorphism and deformation is called a cleavage. A cleavage is especially present if it's in fine-grained rocks where more obvious schistosity isn't visible. Here are some examples of cleavage at different scales and in different rocks. At the hand sample scale on the top right, it's a little tough to see in this image, but the alignment of shadows are getting caught on the cleavage planes that have formed in this rock. The dark and light colored bands of different minerals are actually the original bedding that has been folded and moved around due to metamorphism. The image on the bottom left shows a very nice fold. You can see the original bedding layers that have been folded into this arc shape. And the cleavage are the fracture planes that are cutting through at a high angle to the original bedding. Similarly, in the photo on the right, we can see a nice antiform-synform pair of folds of the original bedding, and the cleavage is the vertically oriented fractures that cut through the bedding and through the rock. So in the case on the right, the pressure was applied to this rock from the left and right to cause the fractures to form normal to the direction of pressure. Here are some diagrams that illustrate the in situ stresses and differential pressures that I've been talking about. The image on the left is from your chapter reading this week, where the top is illustrating a uniform stress that you would get from a confining pressure during burial of, say, sedimentary rocks. As you go deeper underground, you have the weight of the world on top of you, and that corresponds to the overburden stress or pressure, and you would have, in this sedimentary deposition setting, approximately equal pressure from all directions. As you then move to the lower part of the image, we take this undeformed strata or sedimentary rocks and we compress it horizontally during a mountain building event at a convergence boundary or subduction zone. And all of a sudden now we have a directed pressure or a differential stress such that the horizontal pressure is much higher than the vertical pressure or the out of the page pressure, so the rocks will yield to that pressure and fold. There are other kinds of differential stresses as illustrated on the top right. So far I've talked about the compressional stress. We can also have tensional stress, such as what you might find in a rift zone or a divergent plate boundary area. And you can also get shear stress. When you have differential stress, you may see a combination of one or more of these types of stress. As an example in a rock, the granite, as an igneous rock, would have cooled in a plutonic setting that would have had more of a uniform stress. So the mineral arrangement does not have a distinct foliation or preferred orientation. However, the gneiss, shown on the right, has distinct dark and light layers of minerals that are oriented vertically. So that gneiss would have experienced a directional pressure horizontally. Another thing that happens as rocks deform is that one layer of rock may be brittle, where another is quite ductile. And that has to do with the material properties of the rock themselves. As the rock deforms, the brittle layers will break up, and we call this a boudinage. The illustration on the bottom left shows what boudins would look like along the limb of a fold, where you may have what's called mullions toward the hinge of the fold. An example of boudinage or boudins is shown in the photograph on the right. You may think this looks quite a lot like an igneous xenolith, and that's one note of caution when you go to the field to look for mineral assemblages in addition to larger scale features like xenoliths or boudinages to make the correct observations and interpretations of what the geological environment you're looking at is. Let's have a look again at the metamorphic facies. Note that depth increases going up on the y-axis. This graph has a point within the amphibolite facies labeled as T. This point is a defining boundary between a group of aluminosilicate and metamorphic minerals. So this triple point is the intersection of pressure and temperature between zones in which kyanite, andalusite, and sillimanite will form during metamorphism. You'll note the granulite facies of metamorphic rocks is only in the zone of sillimanite. In contrast, the blue schist and green schist facies are in the zone that would only contain kyanite. The Hornfels zones primarily would contain andalusite, and the amphibolite facies becomes rather complex as it contains the triple point. All three of these minerals may exist within amphibolite grade rocks. This is a very powerful tool to use for mapping the metamorphic facies in a region. Here's an example showing Kingston, where just north of Kingston, in the Frontenac terrain, we find ourselves in the hornblende granulite facies. And if you remember from the last slide, the granulite facies is at a high enough temperature and pressure where sillimanite is the only aluminosilicate mineral that will form. As we move northwest toward Caladar, we get into the amphibolite facies, where we find rocks that may contain sillimanite, andalusite, and kyanite, i.e. the triple point. As we get further west from there, we get into the greenschist facies, which has lower temperature, and in that zone, kyanite is dominant. This zoning that we just looked at has a name. It's called isogrades, and these are zones of similar pressure temperature conditions. Since we can determine the pressure temperature conditions of a metamorphic rock based on its metamorphic facies, we can use that to map out regions that have a similar metamorphic grade of rocks. These isogrades delineate the first appearance of a mineral from a new metamorphic facies based on field mapping and what we can observe in outcrops. The example shown on the right from the eastern United States shows the boundaries between the unmetamorphosed rocks in yellow, the low-grade metamorphic rocks, chlorite, muscovite zone, and biotite zone, and increasing in metamorphic grade toward the east, toward the garnets and starlight zones, and the high-grade sillimanite zone. Let's look at a local example of minerals and metamorphism. If we take quartz, which is silica dioxide, plus dolomite, which is calcium magnesium carbonate, what do we get if we put those together? We have the elements calcium, magnesium, silicon, oxygen, and carbon to play with. Remember, during metamorphism, pressure and heat are driving reactions in the rock. Overall, the chemistry of a zone may not change, but the minerals will. Quartz and dolomite put together during metamorphism will result in diopside and carbon dioxide. So diopside is a form of pyroxene that we introduced last week. Coming back to this example from the last lecture, looking at what impurities in dolostones and sandstones do during metamorphism to the resulting rock. A dolostone with some quartz and clay will end up as a marble with some mica and quartz, and an impure sandstone with some dolomite will become a quartzite with some potassium feldspar and diopside. And now we've learned a bit more about the mineral diopside. There's quite a bit of diopside in Kingston. This is an example of the diopside gneiss. It is a paragneiss, which simply means that it was derived from sedimentary rocks. So the sedimentary rocks it was derived from are quartz and dolomite, which fit into protoliths of sandstones and dolostones. From that, you can start to interpret the protolith of the diopside gneiss and the original depositional environment of the sedimentary protolith rocks. A quick side note on terminology. Para, such as paragneiss, means it was derived from sedimentary rocks. You can also have an orthogneiss, where ortho means the rock was derived from igneous rocks. Foliations such as gneissic layering are layered on different scales. When you're mapping in the field, just like some upper years shown on the left, it's important to describe the different layers and thickness of the relative layers in your notebook when you're taking the observations, and look at the mineralogy of all phases of the rock. You can also see layers on air photos. This is on the right, the photo is at a scale of hundreds of meters, and you can see a distinct trend line of the foliation that's captured in the photo of this outcrop. We can have contacts that are sharp or gradational between layers, and they can be planar, as shown on the left, or wavy, as shown on the right. So after all this, you're probably wondering, how do we actually identify metamorphic rocks? The three key points to remember are metamorphic textures, metamorphic minerals, and foliation if present. For metamorphic textures, we have different sizes and interlocking characteristics of grains to consider. As we've talked about, there are many different types of metamorphic textures. For metamorphic minerals, we've learned that certain minerals only grow under metamorphic temperatures and pressure conditions, called the metamorphic facies, and we can then use this to make interpretations of the history of the rock we're looking at. And foliations are the alignment of platy minerals or alternating layers of felsic and mafic minerals, such as gneissic layering. In the next few classes, we'll start to learn about measuring orientations of foliations and other structures in rocks. That will be very helpful to making maps. There are, of course, some caveats with naming metamorphic rocks. Occasionally, for simplicity, we will simply refer to the composition of a metamorphic rock, i.e. a mafic metamorphic rock simply means it has lots of mafic minerals. A calcareous metamorphic rock implies calcite-bearing protoliths, and quartzo-feldspathic metamorphic rocks, such as a quartzo-feldspathic gneiss, form from protoliths that contain a lot of feldspar and quartz that may not have very much mafic mineral content. Occasionally, metamorphic minerals are referred to by their protolith, such as metasedimentary rock. The example shown on the right is a metaconglomerate, or a metamorphosed conglomerate, which is a metasedimentary rock. We can have a metaigneous rock, and we can even talk about a politic metamorphic rock, which would imply a sedimentary protolith. These more general terms are quite often used in the field and may be further refined into more specific names with additional field work, or sometimes even requiring laboratory work to identify all of the minerals and the percent composition within the rock. A final note for today on field mapping of metamorphic rocks. Metamorphism, especially regional metamorphism, affects whole outcrops, but does it affect all units within an outcrop? In the example on the right from the Kingston area, we can see the diopside gneiss, which was cut by a felsic dike, and subsequently both units were cut by a mafic dike. So are these dikes the same metamorphic grade as the gneiss? And this is an important question to ask yourself in the field when you're collecting these observations, because then maybe that will tell us something about the geological history of the outcrop and the age relationships between the units. Thanks for watching. Please add your comments and questions to the lecture Q&A Google Doc that's posted on OnQ. Make sure you finish reading Chapter 7, Metamorphism and Metamorphic Rocks, and please read Chapter 9 on geological structures and mountain building. Thanks for watching. Bye.